Hello everyone, and welcome to the Kinetic Energy Pre-Lab. So up to this point, we have developed math models for elastic potential energy and gravitational potential energy. And so now it's time to move into kinetic energy. Okay, this is the energy storage mechanism for moving objects. Right? Moving objects produce change. They don't store that ability, it's not a potential. Right? They actually are producing change because they're moving. They're changing position. So what factors do you think might affect the kinetic energy stored in a moving object? Well, let's think about that again as the ability to produce change, right? If I threw something at you, what could I change so that it would produce more change? Well, I could throw it faster perhaps, right? So speed, the speed of the object could affect it. What if I threw a tennis ball at you at a certain speed? And then I threw a bowling ball at you at the same speed. Yeah, see, that would also have a different amount of ability to produce change. Right? And that's due to the object's mass. So this is a three-variable lab. So at the end, we're going to assume here that the kinetic energy somehow depends on the speed of the object and the mass of the object. And so the purpose of this lab is to create graphical and mathematical representations of the relationship between the kinetic energy, the speed, and the mass. And the object we're going to use is a cart moving down an incline. Right? We're going to let a cart roll down an incline. And that's what we're going to use as our kind of conservation of energy machine. Right, so here's the cart, and we're going to let it go, and it will, of course, accelerate down an incline, right, as we've seen in the past. But we have one little problem here that we have to deal with. And that is that although these carts are pretty low friction, there still is a little bit of friction with these carts and these tracks. Right? They're not perfect. And that friction will, of course, dissipate a little bit amount of energy, right, during the motion of this cart. And so it's not really ideal. Right? And that makes it hard to deal with because dissipated energy is really hard to measure, right, and to control. So what we're going to do instead, we're going to play a little trick here, right, which is we're going to do a part one to this lab where we are going to figure out what we are going to call the effective angle of the track, theta sub EFF, right? So theta F, right? The effective angle of the track. This is the angle of the track as if it had no friction, right? So if we let the cart go and it accelerates down the hill, right? It's the angle that would give you the same acceleration that the cart actually has in real life if there was no friction. Then we're going to assume there's no friction and do an energy problem and use that angle. It'll be an angle here, right? The angle of the track. And that'll be an angle that's a little bit smaller than the actual angle of the track, right? So maybe if I set this at 6 degrees, our effective angle might be something like 4 or 5 degrees, right? A little bit less. It acts like the angle's smaller because friction is going to slow down the cart a bit, right? It will store some of that or dissipate some of that energy that normally we would have stored as kinetic. So then the question becomes, well, how do we figure out then the effective angle? So here's a little proof for you. Might want to get this down on your lab sheet as we go through it, okay? If we have a cart and it, of course, accelerates down a hill, explodes at the bottom for some inexplicable reason, right? And it's at the effective angle, right? What is that effective angle? Well, let's do a little force analysis of that cart as it's accelerating down the hill. I hope you remember that when we're dealing with something moving up and down a hill, the first thing we do is rotate our axes. And we rotate our axes so that the new x-axis is parallel to the incline, parallel to the motion, so that the cart now accelerates along the x-axis only. It doesn't accelerate perpendicular to the incline, it only accelerates along the incline, thereby making the motion one-dimensional. So again, we're going to take the axes and we're going to rotate them. And notice the angle that we rotate those axes through. Watch it again. Right? We rotate them through the effective angle to get them to be parallel and perpendicular to the incline. Now we're going to draw our forces. Of course, we have a force of gravity acting on the cart, and that force acts straight down. But since it's not on our new axes, we have to break it up into components. So here is f of gy, or as the concept builder guy calls it, the perpendicular component, right? It's the part of f of g which is perpendicular to the track. And then here is f of gx. This is the part of the force of gravity which is parallel to the track. Be careful. Notice that f of gx is parallel to the x-axis. It's not horizontal, right? We're not doing horizontal and vertical here. So look where the right angle is when you're drawing your diagram. Make sure you got the right angle in the right place. And that makes the effective angle right up here, because that is the angle we rotate the axes through. It's important to get the right angle in the right place so that when we do the trig here, we see that the force of gravity is the hypotenuse of this little right triangle. Well, what other forces act on the cart? Well, it's being supported by the track, so there's a normal force. Now remember, normal means perpendicular to the surfaces, so the normal force will act along the y-axis. How big will that normal force be? Hopefully you're saying it will balance out f of gy. Why do these two forces have to balance? Because what is it not doing perpendicular to the incline? It's not accelerating perpendicular to the incline. It's only accelerating parallel to the incline along our x-axis, which is why we rotated the axes. Right? Make all of our acceleration one-dimensional. Now, there is no friction here, remember, because this is the effective angle, the angle that the track is acting like there's no friction, okay? So no friction, so this is it. This is the force diagram. Well, if f of n and f of gy balance out, that leaves us with f of gx as the only unbalanced force. And so f of gx will make the cart accelerate down the incline. Notice it points down the incline, so the cart speeds up as it goes down the incline. If we apply Newton's second law, which says net force is mass times acceleration, right, that f of gx is our net force. And if we do a little trick here, here's our effective angle. Notice that f of gx is the opposite side to that angle, so we would use the sine function. So the sine of the effective angle is the opposite side, f of gx, over the hypotenuse, f of g. Little step of algebra, move the f of g to the other side by multiplication, since it's division. And we get f of gx is f of g sine of the effective angle. If you don't need this step, great if you know enough trig, but if you do, here it is, right? So then let's take that and plug it in for f of gx in our Newton's second law equation. That means that f of g times the sine of the effective angle is equal to the mass times the acceleration. We're getting closer to having an equation we can use to calculate the effective angle. But we're probably not going to know the force of gravity acting on the cart, right? But we can find the mass of the cart. Just have to put it on one of the electronic balances. And we've known for quite a while now that f of g can be substituted into mg, mass times gravitational field strength. Right? F of g is mg. And now look what happens. What do you notice? Yes, the masses cancel. That means technically the acceleration of the cart doesn't depend on mass. A more massive cart will accelerate just as fast as a less massive cart. This is kind of equivalent to Galileo's law of falling bodies here. Why? Well, really we have two kinds of masses. More mass means more force of gravity, so a bigger f of gx, trying to make it accelerate down the incline, accelerate faster. But more mass, in the MA, also means more inertia, more resistance to changes in its motion. And as we've discussed before, we have this inexplicable but important equivalence of gravitational and inertial masses, which allow us to cancel these out of the equation. Right? So mass is not a factor. Move the g to the other side, and we get the sine of the effective angle is the acceleration of the cart divided by the local gravitational field strength, which of course we know is 9.8. And I don't want to know the sine of the effective angle. I want to know what the effective angle is. Right? So to get the effective angle out of there, I have to take the inverse sine of both sides. Right? So the effective angle will be the inverse sine of the acceleration divided by the gravitational field strength, 9.8. Be careful. Make sure you're putting parentheses around it. Right? like I have in mine right here, or do the division first and then take the inverse sign. Right? Also, make sure your calculator's in degrees so that you get an answer in degrees and not radians. So that means if we look at the equation, if I want to know what the effective angle is, I need to know two things. The local gravitational field strength, which we've already done that lab, 9.8, right? Newtons per kilogram to be technical. And I need to know the acceleration of the cart. Well, how can I figure out the acceleration of the cart going down the hill? We've done this before in labs, right? We can use the little encoder wheel on the bottom to create a velocity time graph, and then the slope of that velocity time graph will be our acceleration. And there's a whole bunch of steps for you to follow, right? To hook up your cart with the Bluetooth to the computer and to set up a velocity time graph and to, run it all. It's something we've done before, right? But follow the steps on the lab sheet and it'll show you how to figure out the acceleration. And once you figure out the acceleration, you plug it in and you can figure out the effective angle. Again, the angle that acts like there is no friction. So that when we get to the energy part of the lab now, right, we can kind of treat it as if there's no friction. In the old days, I used to do this by basically lying to everybody. I'd say that the track was tilted at a particular angle, but actually I'd tilt it a little bit extra, right, to try to balance out friction. But this actually, while it's a little more complex, actually works better, all right, to figure out this effective angle. It does take kind of a two-part lab, but it does really help us to balance out and get rid of, essentially, ignore the effects of friction on the lab. So follow the steps on the lab sheet for part one, okay? Once we know the effective angle, then we can get into the energy part. So we're going to do a lab with energy where we are going to compare kinetic energy versus speed with constant mass. So we're going to keep the mass constant by just not changing the cart, right? Not putting any masses on or off, not changing the carts from table to table, right? Just using one cart. So we want to know what's the relationship between kinetic energy and speed. Again, we're going to have this cart roll down the hill at the effective angle, remember. Well, from an energy perspective, right, the cart will start with no velocity. It'll start from rest, and it'll start at a height above zero, and then you'll let the cart roll down the hill. Right? At the bottom of the hill, it'll have a final height of zero and then a speed that's greater than zero. Right? Not after it hits the bottom, right? But as it gets to the bottom, or anywhere really along the hill, right? It has changed height and it's increased its speed. Now, if we're going to do this from an energy perspective, we have to define our system. So let's put the cart in the system. We'll put the track in the system, and we'll put the Earth in the system. Those are all typical objects we've put in systems before. Now, is this system isolated? Remember, in mechanics, that means no external forces. Well, we've already done the force diagram on the cart, right? The forces are the force of gravity, which is between the cart and the Earth, so that's internal, and the normal force, which is between the cart and the track, so that's internal. So yeah, it's an isolated system. And since it's an isolated system, the energy at the top compared to the energy anywhere else stays the same. It is conserved. So we can compare the energies at any 2 points, right, in the motion of the cart down the hill. So initially, when it's at the top of the hill, what is the energy stored as? Is there any kinetic? No, because it's not moving, right? And it's all Eg because it's higher up, right? So it's Egi. It's a whole pie full of EGI. What about at the bottom of the hill? Well, now there's no more EGI, but it's moving. Right? So that means the whole pie is kinetic. And since the energy is conserved, those pies are the same size, right? There's the same amount of energy. And so we can figure out how much kinetic energy this cart will have at the bottom of the hill by calculating how much energy it has at the top of the hill and then using the law of conservation of energy to set them equal. And we know how to calculate the amount of gravitational potential energy at any point on the hill. We use mgy. Right? mgy is, of course, our gravitational potential energy math model that we know. Okay, so we have to do this, a lot of calculations, all right? This lab has a lot of calculations in order to get done. You got to keep track of everything here, but I got a good detailed lab sheet for you to follow. But basically, we're going to figure out how much EK there is at some point down the hill by comparing it to how much EG there was at the top of the hill. And then because we're using the effective angle, we can neglect any dissipated energy. All right? So we know how to calculate this, but we got to talk about what is delta y. Right? The mass of the cart we could, of course, get just by putting the cart onto the electronic balance. There's a place on your lab sheet for you to write the mass of your cart. And then G is our old friend gravitational field strength, a lab we've already done, 9.8 newtons per kilogram. Delta y here, the height or the change in the height as the cart rolls down the hill, right, is this side, right, of this right triangle here, right? Change in the height, or delta y, if you will, is a more traditional way to write it. Well, that's going to be kind of hard for us to measure. I mean, we could try to take a meter stick and measure how far off the table it is. That gets a little hard to do, and where do you measure to and all of that. Instead, remember that the tracks that we use have a scale on it that's right on the track. So we're going to allow the track to roll a certain distance, which we can measure right on this track. Or we can measure it with the encoder wheel, right? The fifth wheel that's in the center of the track, right? That'll allow us to figure out how far the cart goes. If we call it 0 up here, right, then we can figure out where it is as it rolls down the hill, right? So we're going to use the high-tech equipment to do this. And this is the distance. And if you see the right triangle right here, the distance, which is the hypotenuse, is related to delta y through the sine of the effective angle, right? It's the opposite side. So we can then say that the change in the height is the hypotenuse, distance, times the sine of the effective angle. So this is why we did part 1 first, right? We'll know what the effective angle is. We'll know the distance, which is how far the cart's rolled, right? So from that we can find delta y. Once we know delta y, we can calculate the EG, and once we know the EG, we know how much EK it has at the bottom. And then we can use the computer program, graphical analysis, to also figure out the speed of the cart, right? So in order to do that, and there's a whole bunch of steps, right, on the lab sheet if you look at it for this as well, okay? The lab sheet will tell you how to set up a graph of position and velocity versus time. So you're going to see both of these versus time on the same set of axes. And then you'll be able to look at different distances, all right, when the cart's gone certain distances. And again, there's a chart for this on your data table. It's like 10 centimeters, 20 centimeters, 30 centimeters, in meters though, so 0.1 meters, 0.2 meters, 0.3 meters, and so on. And at each one of those distances, you'll be able to read on the graph what the velocity was, right, and write that down. So with one trip down the track, we can actually get a whole bunch of data. It's a pretty slick and high-tech way of doing the lab, but you've really got to follow the steps in order to calculate the right things. So keep in mind that the whole point of this lab is to figure out the relationship between kinetic energy and speed and mass, right? And we're going to do a lab here where we're going to keep the mass constant and look at the relationship between kinetic energy and speed. This is going to take a graph and a linearization, some fairly complex things, and a bunch of calculations. But all of this stuff that I've put on here now is on your lab sheet, right, for you to use. Right? Or you can ask as you go through if you get a little confused along the way. But follow the lab sheet and enjoy this kinetic energy lab.